Hello. Today I'm talking about a new performance analysis API for HPC. The package is called Timemory. We developed it here at Lawrence Berkeley National Lab. And as you probably know, there's a lot of great tools in the HPC ecosystem. The tool that is probably the most similar to Timemory is Scorpy. Scorpy targets the creation of a joint measurement infrastructure. And Scorpy came about because developers recognized that there was ubiquitous redundant functionality within all these tools. They were implementing a lot of the same things in order to provide sometimes whatever feature they specialized in. So, of course, we did that with Timemory. We ended up implementing just about everything in this list. But when we did that, we really focused on creating a toolkit that would be reusable in such a way that the way that we define components and the way we set up tools, the projects can actually reuse them external to our to the tools that we provide. Okay, so our wall clock timer is defined in such a way that if you're not using the other parts of our library, you can actually just use our wall timer. And that goes for just about every single component that Timemory defines, which at this point is about 50 different components. Thus, we believe it has a strong potential to be a common instrumentation framework. And one of the really nice things about it is the perfect type safety. The way that we handle multiple components preserves the types perfectly. There's no casting to opaque types or dynamic polymorphic types. And it happens to be extremely efficient and flexible and modular and extensible. And it supports using multiple tools at the language level. So ultimately, why would you use Timemory? It is a sort of a unique way of encapsulating a measurement and exporting that capability to something that can be used in a standalone way. It makes different tools consistent to use, while also allowing how that tool is used to be specialized in a situation where you need that specialization. As I said, the toolkit probably most similar to Timemory is Scorpy. And so I'm going to focus here on the differences, a few of the differences between Scorpy and Timemory. Scorpy defines a runtime plugin framework that relies on DLSIM and DLOpen. It uses function pointer callbacks and enumerations, and eventually your plugin goes through what's kind of a black box as far as the Scorpy runtime. With Timemory, there is no sort of black box. You can build tools from scratch by simply using whichever parts of Timemory that you want. You can use the tool bundlers that we have and provide all of your own tools, or you can bundle the tools in a new way using the components that we provide, etc. We provide many tools by the library. As I said, we, of course, implemented a lot of the same functionality, but the focus of this presentation is going to be on the toolkit part, because new standalone tools aren't needed, right? We need a better way to deploy these tools. Okay, so we want to create a straightforward modular system for creating new performance measurements and new performance tools. We want to avoid callback and plugin systems because those sort of patterns of creating those tools force the tool to define a specific sort of prototype and layout that downstream tools have to conform to. And we want to avoid enforcing certain return types and certain arguments. We want to just focus on the names of functions. You know, a start member function should be able to take different arguments because you know the name of the function that it's trying to start something. We also want the components to have the freedom to choose data layouts. You know, we don't want to restrict everybody to basically the C types and pointers to C types. A STL map or a fixed compile time array for C++. Those are very useful structures. Okay, so when we're bundling multiple tools, we're going to run into obviously some issues because some tools require different types of measurements. Certain tools have a start and a stop in order to provide a sort of really relevant data, and then other measurements are atomic. And so those atomic measurements require data being passed in. Okay, so yeah, that particularly is one reason why we don't want specific function prototypes. It's because specific function prototypes make providing data to the framework difficult. Okay, it's just hard to extend that for everybody's use case scenario. So the approach we've taken is the component bundlers they're variadic templates. So you have a class which is a variadic template, and it takes the template parameters of the components that you want to measure. And these components can nest each other. You know, you can have a component that implements other components. You can have a component that does your DL send callback system if you want. Okay, and all the member functions of these component bundlers are also variadic, meaning that you can pass to these component bundlers any arguments that you want. And it's up to the components to essentially decide whether or not they accept, say, start with those arguments. Okay, and we do that by compile time checks. And doing that at compile time makes for a very efficient system. Additionally, whenever you're stringing together multiple tools, multiple capabilities, the capabilities aren't always going to be available in every single situation. Either the package isn't installed or it's not available on that operating system, etc. Okay, so we don't want these types that aren't available to cause extra overhead, and we definitely don't want a whole bunch of preprocessors, because with those variadic templates, that would just sort of be a mess. But templates have this sort of nice little feature where you can list a type in a template, but if you never actually instantiate it, then you don't actually ever need the definition. Thus, all Timemory really needs is a declaration of a type and then a way to filter out that type so that it never gets instantiated. Okay, this solves a lot of our multiplexing issues. Okay, so we provide basically 3 different component bundlers. We have a tuple, which allocates all the components on the stack. This tends to be the most performant at runtime. We have a list, which allocates those components on the heap and provides for a lot more runtime configurability. And then we have a component bundle, which is essentially allows something like a list and a tuple together with an extra template parameter to turn all of the tools off. And then we have essentially 3 duplicates of those that take the original functionality and then wrap the call to start and the call to stop on all the components within their constructors. And we call those the auto tuple, the auto list, and the auto bundle. So now that I've explained component bundlers to you, here's what it looks like in practice. We have a component tuple of 5 different tools. We simply just create that type and we pass in that string, which is a label that gets propagated to all 5 tools. We call start on that object that starts all 5 tools. Within this loop, there's a call to a mark begin member function and a mark end member function. And we pass in a CUDA string. Logically, that you can assume that stream doesn't have any relevance to a wall clock, a CPU clock, or a CPU utilization. Thus, within that loop, we actually only, that member function mark begin is only provided by CUDA event and MVTX marker. So it's a demonstration about how you really don't have to do anything special with these component bundlers. You don't have to worry about whether or not a component supports a certain operation. The bundler takes care of making sure that you don't have any compile time errors, and it'll just silently eliminate that call for your components when they don't support something being called on there. That declaration of a component is actually a very nice property because we can create a very simple system so that tools that want to provide Timemory support can simply provide us with a simple little header like you see here. And then they can maintain their component in their package and just in a header that we would later include if somebody turned it on. And, because we don't enforce, specific types, the components really are standalone. You don't really need that definition for Timemory. They take strings, etc., stuff like that. For example, here is what a town marker component definition look like. And if you take a look here, there's not too much to worry about here as far as compatibility goes. There's no Timemory defined type that they are using. They look like just regular functions taking standard C and C++ values and returning regular C and C++ values. And Timemory simply can adapt to the return types and the arguments that the interface provides when Timemory is compiled. And here we actually combine sort of the start and stop phase with events in tau, even though for tau these are quite separate. We were able to combine them in Timemory, but you could actually make 2 different components for tau. Here's another example of a component definition for hardware counters, where we reuse another component. So Timemory, one of the callback components we provide is POPI support. and there's a fixed poppy type called a poppy tuple. There's also dynamically allocated ones, but there's a fixed one where you can specify for sort of optimal performance which hardware counters that you want, and you can fix that size of compile time. So in this particular example, we are using the fixed size. We are basically specifying we want the hardware counter for double precision operations and the load store instructions. Okay, we're going to store that in a basically two long entries. Okay, and as you can see in the start, we just simply create that poppy tuple component as part of our flops per byte. And in the start member function, we call start. On our poppy tuple, we call stop. And then we, this is for the nice thing about Timemory is the get member function is the value type that it returns is not really related to the storage type at all. So you can store in sort of an optimal way, and then when you provide a get function so that people can get access to that data, you can return and the data type that is actually representative of the value, right? And then here down at the bottom, we provide just this Timemory register flops per byte. That's sort of a special function for the instrumentation, and the instrumentation uses this thing called a user trace bundle to insert instrumentation around function calls. So objects of user trace bundle type get injected into the binary, and here we are providing essentially a callback so that when we build our custom instrumentation with something like this CMake that you see here on the left, we can just use Timemory run to load that library. And what will happen is right after the call to main, Timemory will inject the call to Timemory register flops per byte, and user trace bundle will get configured with our new tool. Okay, and this new tool that you have will fully support essentially everything else that all the other components support. It's a fully integrated component at this point. JSON output, hierarchical storage, MPI support, multi-threading support, etc. Just essentially anything that a standard Timemory component supports, this component here would support. Okay, so you can see it's a very easy way for defining new capabilities. Okay, getting a little low on time, so I'm just going to say that this presentation doesn't cover some of the novel use cases that we presented in the paper. I'd encourage you to read it. One particularly interesting one is where we use the Timemory toolkit within a physics toolkit to create a custom API for the users of the physics toolkit to create an object-based measurement framework. Another one is how we can build a precision a tuner for a mixed precision library. Okay, there's in the recent Timemory versions, there are sampling capabilities that have been updated since the paper. We didn't cover, we provide standard macros and stuff like that. We have the library interface, Python interface, visualization, new instrumentation stuff. Timemory actually has the potential to be an output conversion tool between different tools, so that you can get, maybe your favorite tool converted into the output of your favorite profile of doing. So there's potential there. And we also sort of skipped over sort of the capability that Timemory provides for per thread and per process aggregation or separating them out. And we're just going to sort of summarize up what we saw in this presentation. There was, we provided a language level compatibility between tools with different features and different layouts. Okay, we showed how components are self-contained, they're reusable and composable, and they can define their own interface while also having a standard method for providing direct access to the data. Direct access to the data is important because that's really how it gets utilized by other frameworks. Okay, and we also talked about the variadic bundlers, and you may have noticed they really do emulate components. They have the same sort of member function, and that's you can actually nest components, component bundlers within component bundlers. And you can see how they optimize the function invocations by making a lot of decisions at compile time. They also have different features for allowing tools to be fixed and optimal at compile time or selected at runtime. And we really believe this will help eliminate a lot of the redundant implementations. And we can provide a lot of easy to integrate tools into new APIs and add new capabilities much more quickly than we are currently doing now. I'd like to thank you for your time. If you were looking to check out Timemory, it's at github.nurse.timemory. There's some read the docs. We have a package available on SPAC and PyPy. Thanks to our sponsors and our digital media sponsors. Thank you very much.